Welcome to WikiPodcast. Today, we're doing a deep dive into something fundamental, light. Specifically, how it interacts with the world, how it bounces, how it bends.
That's right. We're venturing into optics, looking at reflection and refraction. These are the core ways light behaves when it hits something or passes through different stuff.
And our mission really is to unpack why things look the way they do. Why mirrors work, why a straw looks bent in a glass of water.
Exactly. We want to give you a clear understanding of those fundamental principles.
And to get started, we're going to use a concept from physics called geometrical optics. Sounds a bit technical, but it's actually a simplification, right?
It is, yeah. Geometrical optics, or sometimes called ray optics, it's basically a model where we think of light traveling in straight lines. We call these lines rays.
Not like actual beams, though.
No, not physical things. Think of them as abstract lines representing the path light takes. It's a really useful approximation, especially when light hits things much bigger than its own wavelength.
If it's most everyday objects.
Right. Pretty much everything you see directly, yes. Mirrors, lenses, your eyes. This model works incredibly well for those. It helps us trace the path of light without getting bogged down in the full wave complexity.
Okay, so these rays, they're lines showing direction. You mentioned they're related to wavefronts.
Yeah, think of ripples spreading on water. Those are the wavefronts. The rays are lines drawn straight out, perpendicular to those ripples, showing which way the energy is going.
And why do they travel in straight lines in, say, empty space or air? Is that just assumed?
It actually comes from something deeper, a really neat idea called Fermat's principle.
Fermat's principle. Sounds familiar.
It's the principle of least time. Basically, it says that between any 2 points, light will take the path that takes the least amount of time to travel.
Huh. So light is efficient.
In a way, yes. In a uniform medium like air or vacuum, the speed of light is constant. So the path that takes the least time is just the shortest distance, a straight line. So the ray model follows from this optimization principle.
That's fascinating. Light's always taking the shortcut.
Pretty much. And geometrical optics builds on this with a few key ideas about these rays. They go straight in one material.
Right.
They bend pretty sharply when they cross from one material to another, like air to water.
Okay.
They can follow curved paths if the material itself changes gradually.
We'll get to that, I bet.
And of course, light can be absorbed by a material, or it can bounce off. That's reflection.
But it's still a model, an approximation. What does it miss? What are the limitations?
Good point. It's great for lenses and mirrors, but it doesn't explain everything. Things like diffraction, how light spreads out when it goes through a really narrow slit, or interference, where light waves can, cancel each other out or add up. Those need the full wave picture, what we call physical optics.
Got it. So geometrical optics for the big picture of bending and bouncing.
Exactly. It's the right tool for this job.
Okay, let's dive into that first big behavior then, reflection, bouncing off.
Right. This is fundamental to how we see almost everything. Light from a source hits an object, bounces off, and travels to our eyes. When that surface is smooth, like a mirror, the bouncing follows a very clear rule.
Which is the law of reflection.
Precisely. Imagine the point where the light ray hits the surface. Now, draw a line perpendicular to the surface right there. That's called the normal.
Okay, the normal, like 90 degrees to the surface.
Exactly. The incoming light ray, the incident ray, makes an angle with that normal. The law of reflection says the outgoing ray, the reflected ray, bounces off, making the exact same angle with the normal, but on the other side.
Angle in equals angle out.
Angle of incidence equals angle of reflection. And crucially, the incoming ray, the outgoing ray, and that normal line all lie on the same flat plane.
Simple rule, but powerful. How does that explain my reflection in a bathroom mirror? It looks so perfect.
It's because your brain assumes light travels in straight lines. When the reflected rays from, say, your nose hit your eye, your brain traces them back in straight lines behind the mirror.
How?
And because of that equal angle rule, those traced back lines converge at a point that seems to be the same distance behind the mirror as your actual nose is in front. Do that for every point on your face, and you see a complete image.
Which is why it's upright. Same size.
Exactly. And it appears the same distance behind the mirror.
What about the left-right flip? That always messes with my head.
Yeah, that's interesting. It's often called left-right inversion, but it's more accurately a front-back reversal. The image is reversed along the direction perpendicular to the mirror surface, the depth axis.
So if I point up, the image points up.
Right. But if you point towards the mirror, the image points out from the mirror towards you. It's that depth reversal that makes your right hand look like the image's left hand when you face the mirror.
Okay, that clarifies things. Now, curved mirrors. This is where it gets fun, like funhouse mirrors or telescopes. Does the same law apply?
Absolutely. The law of reflection holds true at every single point on the curved surface. The trick is that the normal line is different at every point because the surface is tilted differently.
Right, the surface orientation changes.
Exactly. So parallel rays hitting different parts of the curve bounce off according to the local normal, and they don't all go in the same direction like with a flat mirror.
And this leads to focusing,
Right.
especially with parabolic mirrors.
Yes. Parabolic mirrors have this amazing property. If you shape a mirror like a parabola, any light rays coming in parallel to the mirror's central axis will all reflect and converge perfectly at a single point, the focal point.
Which is why they're used in satellite dishes.
And reflecting telescopes, yeah. They collect parallel light from distant stars and focus it. Car headlights use them too, but in reverse, put a bulb at the focus, and the mirror reflects the light into a parallel beam.
What about spherical mirrors? They seem more common, like those security mirrors in shops.
They are easier and cheaper to make, just a section of a sphere. They do focus light, roughly, but not perfectly like a parabola. They suffer from something called spherical aberration.
Aberration, meaning an error.
Yeah, a flaw. Rays hitting the outer edges of a spherical mirror don't focus at exactly the same point as rays hitting near the center. The focus is a bit smeared out, which makes the image less sharp.
Ah, like the Hubble telescope issue they had to fix.
That was famously a case of spherical aberration, yes. They needed corrective optics.
And these curved mirrors, they can make images look bigger or smaller and sometimes upside down.
They can. Depending on the mirror's shape, concave or convex, and how far the object is, you can get magnified or reduced images, and they can be upright or inverted.
And there's this difference between virtual and real images.
Right. The image in your flat bathroom mirror is virtual. It appears behind the mirror where the light rays don't actually converge. You can't project it onto a screen.
Yeah.
A concave mirror, like a makeup mirror, if you're close enough, also shows an upright, magnified virtual image. But if the object is further away, it can form a real image in front of the mirror where the light rays actually cross. This image is typically inverted, and you could project it onto a piece of paper if you held it at the right spot.
Like in an old school projector. Okay, that covers reflection. Let's switch gears to the other big one. Refraction. Light going through stuff and bending.
Exactly. Refraction is what happens when light passes from one transparent medium into another, say from air into water or air into glass. The key thing is the speed of light changes.
It slows down in denser materials, right?
Generally, yes. Light travels fastest in a vacuum. In any material, it slows down. This change in speed is what causes the bending.
And we measure that change with the index of refraction.
Yep, the index of refraction, usually written as n. It's just a number that tells you the ratio of the speed of light in a vacuum to the speed of light in that material. Air is very close to 1, water is about 1.33, glass is around 1.5 or higher, diamond has a very high index, about 2.4.
So higher end means slower light.
And more potential for bending, yes. The interaction of the light's electromagnetic field with the atoms in the material causes this effect of slowdown.
And the rule governing how much it bends is Snell's law.
That's the one, named after Willebrord Snellius. It's a mathematical formula, n sin he hen ia, but the idea is straightforward. It relates the angle of the incoming ray in the first medium with index n to the angle of the bent ray in the second medium, index n ray. Both angles are measured from that normal line again.
Okay, so what does it tell us? If light goes from air, low n, to water, high n.
It bends towards the normal. The ray gets steeper, closer to perpendicular. If it goes the other way, from water high n to air low n, it speeds up and bends away from the normal.
And the bigger the difference in n, the more it bends.
Exactly. That's why a straw in a glass of water looks bent or broken at the surface. Light from the submerged part travels from water to air, bends away from the normal, and your eye traces those rays back to an apparent position that's shallower than the real straw.
Simple law, big consequences.
Yeah.
Total internal reflection. Sounds dramatic.
It is pretty cool. This only happens when light tries to go from a higher index medium to a lower index one, like from glass back into air.
Okay, going faster.
Right. As it bends away from the normal, if you make the incoming angle steep enough, the bent ray in the air would have to bend away more than 90 degrees, which is impossible.
I can't get out.
Can't get out. Beyond a certain critical angle of incidence, None of the light refracts out. It all gets reflected back inside the denser medium, 100% reflection. That's total internal reflection, or TIR.
Wow. And that's how fiber optics work.
Precisely. A fiber optic cable is a thin strand of very pure glass or plastic, the core high index, surrounded by another layer called cladding, a slightly lower index. Light signals are shown into the core at an angle greater than the critical angle.
So they hit the boundary between core and cladding.
And totally internally reflect. They just bounce their way down the fiber, even around corners, with incredibly low loss of signal. It's TIR that lets us send internet data across oceans in these cables.
Amazing. Just light bouncing inside a tiny glass thread.
Billions of bits per second.
Okay, another consequence of refraction. Prisms and rainbows.
Yeah.
How does Snell's law explain splitting white light?
Dispersion. This happens because the index of refraction in, for most materials, isn't exactly the same for all colors or wavelengths of light.
Oh, right. Different colors have different wavelengths.
Yep. And it turns out that typically the index N is slightly higher for shorter wavelengths, like blue and violet, than for longer wavelengths, like red.
So blue light slows down a tiny bit more than red light in glass?
Exactly. So when white light, which is a mix of all colors, enters a prism, each color refracts according to Snell's law, but using its own slightly different N. Since blue light has a higher N, it bends more than red light.
And they separate out?
They spread out into a spectrum. Violet bends most, red bends least. That's how a prism creates a rainbow, and it's famously how Isaac Newton showed that white light is actually made up of all the colors.
Brilliant. Now, you also mentioned light can follow curved paths, not just straight lines or sharp bends.
Yes, if the refractive index isn't uniform but changes gradually within a medium, this is called a gradient index or Grin effect. Light rays will continuously bend towards the regions where the refractive index is higher, where light travels slower.
Like a mirage on a hot road.
Perfect example. The road heats the air just above it, making it less dense. Cooler, denser air is higher up. Less dense air has a slightly lower refractive index than denser air.
So there's a gradient. Low near the road, higher and further up.
Right. Light from the sky coming down towards the road enters this gradient, continuously bending away from the hotter, lower region near the road. It curves upwards towards your eye.
Making it look like the light came from the road surface, like a reflection of the sky.
Exactly. That shimmering puddle is actually an image of the sky caused by light bending through the hot air gradient. Gyrine materials are also engineered for things like photocopiers and scanners now to make compact lenses.
Okay, this bending, this refraction, it leads us straight to lenses. Devices designed to bend light.
Precisely. Lenses use curved surfaces and refraction to deliberately manipulate light rays, usually to either focus them together or spread them apart.
And the two basic types are convex and concave.
That's right. A convex lens is thicker in the middle, like a magnifying glass. It converges parallel light rays, bending them inwards to meet at a focal point on the other side.
And a concave lens.
Thinner in the middle, thicker edges. It diverges parallel rays, bending them outwards so they appear to spread out from a focal point on the same side the light came from.
And just like with mirrors, we can figure out where images form.
Yes, often using ray tracing, or, more conveniently for simple cases, the thin lens equation. This assumes the lens thickness is negligible compared to other distances.
That's the 1 over S1 plus 1 over S2 equals 1 over F1.
That's the one. S is the object distance, S is the image distance, and F is the focal length, a property of the lens itself, telling you how strongly it converges or diverges light.
And there are rules for positive and negative signs.
Yeah, sign conventions are key. Typically, object distance SO is positive. Focal length F is positive for a convex converging lens, negative for a concave diverging lens. Image distance SO is positive if the image forms on the opposite side of the lens from the object, a real image, and negative if it forms on the same side, a virtual image.
Okay, keep track of everything. And magnification.
There's an equation for that too. Magnification M equals minus S-zeros divided by S-zero. The value tells you the size ratio, and the sign tells you orientation. Positive M means an upright image. Negative M means an inverted image.
And for single lenses, upright always means virtual. Inverted always means real.
That's a good rule of thumb for single lenses, yes. A magnifying glass gives you an upright virtual image. A slide projector lens gives you an inverted real image on the screen.
But lenses, like mirrors, aren't perfect either. They have aberrations.
Correct. They suffer from similar geometric issues like spherical aberration, where rays through the edges don't focus at quite the same spot as rays through the center. But they also have a unique one, chromatic aberration.
Chromatic color.
Because of dispersion.
Exactly. Since the refractive index varies slightly with color, a simple lens will bend blue light a bit more strongly than red light. This means different colors focus at slightly different points,
Leading to color fringes around bright objects in photos, maybe.
That's often chromatic aberration, yes.
Yeah.
High-quality camera lenses, microscopes, telescopes use multiple lens elements made of different types of glass cemented together to cancel out both spherical and chromatic aberrations as much as possible.
It's amazing how complex it gets to make a perfect image. So we've talked rays, reflection, refraction. But how does this simple ray model really connect back to the fundamental nature of light as an electromagnetic wave, described by, like, Maxwell's equations?
That's a great question. Geometrical optics isn't just a handy trick. It's actually what emerges from the full wave theory, from Maxwell's equations, in a specific limit.
What limit is that?
The limit where the wavelength of the light is very, very small compared to the dimensions of the objects it's interacting with, the mirrors, the lenses, the openings. So for everyday objects, the wavelength is tiny.
It is. Visible light wavelengths are measured in nanometers, hundreds of billionths of a meter. Mirrors and lenses are millimeters or centimeters or meters across. In that situation, the wave behavior, like diffraction, becomes less significant for just tracing the main path of the light energy. The wavefronts essentially propagate along paths that look like rays.
So the rays are like the direction of travel of the wavefronts.
Precisely. They are lines drawn perpendicular or orthogonal to the wavefronts. And the mathematical derivations show that these paths, these rays, naturally follow Fermat's principle of least time. So the simple rules we've discussed, reflection, refraction, Snell's law, they actually arise from the deeper wave physics under these common conditions.
It all ties together. Okay, let's bring this home. Why does understanding reflection and refraction matter to, someone just going about their day?
Oh, it's everywhere, constantly. Every time you see a reflection in a window or a spoon or a puddle, that's reflection.
Looking through eyeglasses or contacts.
That's refraction, bending light to help your eye focus correctly. The lens in your eye itself uses refraction to form an image on your retina.
The bent straw illusion we talked about.
Classic refraction. Cameras creating photos, telescopes showing distant galaxies, microscopes revealing tiny structures all rely on lenses, and sometimes mirrors carefully manipulating light through refraction and reflection.
Fiber optics bringing us the internet.
Pure, total internal reflection. Even a rainbow after a storm, that's sunlight refracting and dispersing through millions of tiny water droplets acting like prisms.
And that weird shimmering mirage on the highway.
That's the GRN effect, light bending through gradually changing air density and refractive index. Our entire visual perception and so much of our technology is built on these two fundamental interactions of light with matter.
So we've covered a lot: reflection off surfaces, refraction through materials, how these simple rules explain mirrors, lenses, fiber optics, rainbows, mirages, even how our eyes work. It's kind of amazing how these principles are just constantly at play.
It really is. Think about how much we rely on controlling light this way, from simple mirrors to complex optical instruments and global communication networks. It's all just bending and bouncing, fundamentally.
Makes you wonder what other subtle optical effects are happening around us all the time that maybe we don't even consciously register.
Yeah.
That shimmering heat haze, the sparkle off water, governed by the same rules. Definitely food for thought. Thanks for listening. Write us your opinion in the comments on what is the most surprising application of light bending you've encountered. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.